Here we are going to find out what does it take to build an autonomous vehicle. And we have with us Dr. Arjun Jain. Dr. Jain is an adjunct faculty at the Center for Data Sciences at Indian Institute of Science. He received his PhD in computer science from Max Planck Institute for Informatics in Germany and worked with 2020 Turing Award winner Max Yan Li-kun during his postdoc at NYU. He's a part of the Theano development team and a contributor to Torch, both of which are widely used libraries for deep learning. Dr. Jain is also a founder of UAVIO Labs and Fast Code AI. He previously founded Perceptive Code LLC and a Silicon Valley startup that builds intelligence into automobiles. Arjun has worked for several companies, including Yahoo in Bangalore, Beta Digital in New Zealand, and Apple in Cupertino. He's been especially active in the human sensing related industries. Arjun served as a developer for Beta Digital's motion capture system. This system has been used in many feature films, and Arjun was credited for his work in Steven Spielberg's The Adventure of Tintin. Yes, you heard that right, ladies and gentlemen, in 2011. Arjun's work has resulted in several academic publications with currently over 5,000 citations, patents, and has been featured by mainstream media, including the magazines New Scientist, Discovery, BBC, Vogue, Wired, India Today, and The Hollywood Reporter, amongst many others. So members of the audience, with a huge round of applause, please help me in welcoming Professor Arjun Jain on the screen.
Thank you, Fatima, for that very kind introduction. I would start with sharing, okay, let me share my screen. Let me share my entire screen. All right. So without further ado, let us get started. So, like you know, the topic for today is what does it take to build an autonomous car? So I want to give you some background and then show you the various subsystems, the challenges, and what we're working towards, right? So what will it finally take to get these cars in all parts of the world? Now, so I hope you can see my screen. Maybe let me minimize this thing. All right. Yeah. So, so there are usually, so there were these two main trends in automotive. And so there was the user comfort and assist, which we call the interior of the car. And then, of course, the exterior of the car, or the autonomous driving itself. Now, the user comfort and assist was a lower hanging fruit. And we successfully, implemented it in the car. You can buy it as a feature in the Mercedes-Benz, for example. So the company that I sold to Mercedes-Benz was used to build this system. This is Volker Entenmann at the Paris Auto Show. He was our program manager, and he's demoing the system. So we installed a camera just behind the rear view mirror. And based on that, we can realize a few user comfort or UI-based use cases. For example, we can distinguish between the driver and passenger hand. And now, since the passenger is touching or playing with the touchscreen, the corresponding seat gets highlighted. It's not just, so you now see the passenger interacting or the driver interacting. So based on that, so this is one click less. Not just the touchscreen, because we can localize the hand position in the entire cockpit. Even when he takes his hand close to the touchpad that you see there below, the corresponding seat gets highlighted. There are also some gesture-based use cases. For example, if you tap below the rear view mirror, the light gets switched on. There is a favorite pose, and so on, right? So this was 2018. Then in 2020, we installed cameras. So this is the Mercedes-Benz top-line car, the Maybach S-Class. And we installed cameras not just in the front, but also in the rear. And with this, we could also perform, these kind of use cases where you just have this swipe gesture and the door gets automatically closed. Also, the seat belt presenter is difficult to reach, and you can do this and it just presents itself. Also the sunroof and so on. We can also, so this was the light feature that I was talking about. One feature which I do not show here, which is also very interesting, is you can automatically choose the rear view mirror which you want to adjust by just knowing the head pose. So it is one click less, and they've actually removed that middle button, right? So the choosing button. This led to a lot of publications in major conferences like ICCV, ACCV, ECCV, and so on during our work. Now, the question was, like, so this is still the easier use case because this is not safety critical. But of course, the motto of Mercedes is best or nothing. So it just cannot fail. I mean, maybe the failure rate can be 1 in 1,000. So if it fails 1 in 1,000, maybe it's still okay. But more than that, they will not put it into their cars. But the question that we probably you have in your mind is, like, why did it come so late? Because for example, work from Chris Bregler back in 1998, they could already do this human pose estimation. Also, my own work back in 2010, we could do a full body tracking using single or multiple cameras. So as you saw, the applications that, the previous applications, we need to estimate the position of the hand joint in 3D within the car. And we've been trying to do this for a long time. However, the performance was not good enough for industry. And then, as you all know, in 2012, AlexNet happened. And 6 years after AlexNet, we could have it in the car, right? So this is still interior of the car. We've been working in parallel with also, the autonomous driving teams at Mercedes, Bosch, and Volkswagen. And so this is one of our papers where we do, human pose estimation for multiple people for use cases such as identifying, what gesture is being performed by a traffic policeman or a school guard and so on. And these are, so this is the speed versus accuracy curve. So lower is better accuracy. And on the x-axis, you have, the timing. So lower is better. And here also lower is better. So the model here is what we want to get to. So we've started with this baseline A, and we could get to, a model here. Now, so the point here I wanted to show you is that this is something which is already done, and not just by Mercedes, but by a lot of other companies. And so this is done and dusted in the interior of the car. Now let's move to the more challenging and interesting use case with obviously a bigger impact, which is autonomous driving. And before I start and show you, the entire stack and what we have done, I want to show you some interesting history. Just to show you that, again, like human pose estimation, autonomous cars are also not new. I mean, it has been going on. So the Prometheus project in Europe, let me switch on my pointer. Yeah. So the Prometheus project in Europe was started in 1987. And here you see this Vita 2 by Daimler-Benz, which could already drive almost autonomously on the highway. And then all of you, I'm sure, are aware of this DARPA challenge in 2004, which was the first major automated driving competition. And the most interesting part, which you may not know, is that all participants failed to complete the 150-mile off-road track. Now, the ask here was also difficult. The ask was that, there should be no human intervention at any level for this 150 miles. So none of them succeeded. Then there was a similar DARPA challenge the next year in 2005. And this time, 5 teams managed to complete the track. Now, what was the major difference here? Velodyne, the well-known LiDAR company, right? So they sell these LiDAR sensors. They supplied these sensors to all the 5 winning teams, right? So there was this big leap in terms of the sensor. And feel free to ask me. Is there a question? Oh, all right. So feel free to ask questions, and yeah, we can have an interactive session, and I'll stop and answer your questions before moving on. Yeah. So yeah, Velodyne came and changed the game. And then in 2007, they also did, urban kind of an environment. So they did this DARPA Urban Challenge in 2007, which was modeled after a typical urban scene, and 6 teams managed to complete the event. But the difference here was that, it was not a typical urban scene in the sense the objects were all static. So there were no moving pedestrians or other cars that they had to worry about. So the point here being that, this has been going on since 1987. And we are here in 2021 and we are still not, like we still don't have full-scale autonomous cars which can go everywhere. So now, after we know about the history, let's now see what it takes to go autonomous. So you can do autonomous in 2 ways, either as a ego-only system or as a connected system. So previously you were talking about IoTs and connected systems. So what is the difference between ego-only and connected autonomous vehicles? Ego-only is where you will trust only your observations and you have to navigate on the road based on only your knowledge and observation. But connected systems are where, you will also use observations from other vehicles which you are connected to via network. But today we focus, today in the industry, we focus only on ego-only systems because of course, safety and robustness issues, because we do not want to rely on other systems and so on, right? And so this is what we will basically be talking about in our talk today. Now, also, autonomous systems can be of 2 types, either end-to-end systems or modular systems. So I'll first talk about end-to-end systems. So end-to-end system is where, you treat the automated driving use case as a black box, and in comes, your camera feed. So your camera video, your sat nav input, and that's it, right? It goes into a black box, a big, deep neural network, and out comes these driving commands, right? So this is end-to-end deep learning, and out comes driving commands such as how much should you steer, should you brake, should you accelerate, and that's it. And later I'll show you companies which are trying to do these and where they are. But we will first start with the more widely used system, which are modular systems. And modular systems are roughly composed of these 5 modules. The first is perception. We'll go into all these in detail in the next slides, right? So perception. Then there is scene representation and localization. Then there is prediction, followed by planning and decision making, and finally vehicle control. So now let's look at each of these modules in detail. Now, perception. So the dictionary definition of perception is the ability to see, hear, or become aware of something through our senses. And similarly for a robot or an autonomous car, the senses are essentially things like, LiDAR, vision, also a little bit of sound and so on for detecting emergency vehicles, police cars and so on. But let's focus on the vision perception, right? So the feed coming in through the cameras. So a typical frame from the camera could look something like this. And the point I want to make here is, I want to show you how complex this system needs to be able to identify what all is going on. As a human, we can all drive and we are, very good at doing these kind of things. But for agent on the car, it needs to identify things like moving objects. So it needs to know that, okay, there's a car in front of me. It also needs to know the direction, that, okay, this is going in the same direction as me. Maybe this one is going in the opposite direction. It needs to know that there's maybe a something parked on the side of the road. It needs to detect static objects. It needs to detect, static objects and then classify them into road signs. It needs to find these overhead road signs, traffic lights, and their state. Is it red, yellow, or green? It needs to know the lane lines, also the kind of lane lines, solid, dotted, yellow, double yellow. It needs to know road markings. Okay, so it says wait. It needs to know the curb, because curbs are special, because you find pedestrians, which are the most important objects on the road, right? Because they're humans. Then there are, you need to identify crosswalks, You also need to identify if we are in a residential area, are we in a tunnel, are we approaching a toll booth, and so on. So you see that the problem is complex. And next, I will take a simple, I will only take this moving objects part, right? So let's now dig deeper into the moving objects. So moving objects can be of various types, right? So it can be overturn, like a vehicle which is not moving anymore because it met with an accident. It can be a human, it can be a rider, it can be a car, a pickup truck which looks like this. It can be a truck which looks almost just white. It needs it, it can be a person with a pram and so on, right? So many different kinds of moving vehicles. And it also has additional subtasks. For example, it needs to know the object type, vehicle classes, blinkers, brakes. So the state of blinkers, is it blinking? Is it the left indicator? Is it the right indicator? Or is he pressing the brakes? Is the car parked? Has it met with a collision? And so on. So moving objects itself is difficult. And now I will focus on a subtask from here. So only cars. We'll not look at pedestrians or riders. So even just cars can be very difficult, right? So for example, they can look very different for the machine. So here you hardly see the car, you just see the body. Here it's a completely different case. Here it has, it is overturned and so on. So even a single subtask, car detection, is a very difficult problem. And note that 97% is not good enough for automated driving. Finally, after fusing multiple sensors together, we need to get to almost 100%. Yeah. And I'll show you. So this is another use case, which is traffic sign detection and recognition. And again, with the challenges with such systems are you need high accuracy. It should work without HD maps. And the biggest problem with traffic sign is the data imbalance, because some signs are rare and have very few examples, but still are very important, right? So you may have classes with hundreds of thousands of examples and classes with maybe only 30 examples. So how do you deal with this data imbalance? And finally, you need a low latency, high accuracy system. And this is what a typical traffic sign detection subsystem may look like. So you will have a detector on the entire frame, which will detect a traffic sign, and it'll maybe classify it into a few, coarse-grained classes, because you can, so if there are 600 traffic signs, you cannot ask the detector to give you all the 600 classes. Then after you get the crop, you can then send it into a classifier. You may also need to run OCR on it, because some signs are text only, specifically in the US, or you may need to read the the name of the city or town and so on. Then you need to associate it with a parent sign, because one sign can have multiple signs on it and so on. So it's complicated. So that was perception, right? So perception itself is very complicated. Now, the next one is scene representation. So here you see that after the vehicle senses and observes the world through its sensors, as you see below, it then needs to put all the sensed objects and itself into a coherent 3D map, right? So this is the scene representation, where you represent the scene and yourself in the scene. So you see that it has successfully represented the scene here, and then it has represented, there's a cross, there are these vehicles represented by these purple boxes, and so on and so forth. So this is scene representation. The next step is localization. So, you've represented the scene, but then you need to localize yourself in the scene, and also keep doing that at every time step, right? So here you see a LiDAR map. So this is what the LiDAR sensor sees. And the typical and the most accurate way to do localization is by first creating a high resolution, high fidelity 3D map of the world, and then take these local measurements by your LiDAR sensor, and then find where in this world does your current observation fit best, right? Because GPS, etc., is not as accurate as we would want it to be, right? Because in driving, you need to be accurate up to, say, a few centimeters, but GPS can only be, say, accurate to, say, half a meter or 1 meter. So this is the most common way of doing localization. Then, so this is when you have the luxury of LiDAR. Now companies are trying to do it without LiDAR or even radar. Uh, so Tesla is one of them. For example, Tesla only sees these images, and based on that, it has to localize itself in the world, which is a very difficult task. And it doesn't actually do this. It bypasses this step. We'll not go into that, but yeah, so it has to still make sense of the world and where it is in the world using what it sees, right? Next, after we've done,
bicycle will go straight through the red light.
Sorry about that.
And it could also believe.
Yeah. So now, so this is important, right? So now what we've done is we have sensed the world. We know what lies in front of us or behind us. We have also represented that in a 3D world. We have put ourselves in the 3D world. Now, what is the next step? So what we need to do next is we also need to predict where objects will be in the future. Why? Because we have very little time, because we're moving fast and the distances are small. You don't need to do this, for example, for drones, because in drones, you assume a static world and also the distances are not as close, right? So unless you're doing swarms, etc. So here, for example, there is a bicycle which you detect here. Now, for this car to decide if it should go straight or not, it also has to predict if the bicycle will go straight or will it turn right or will it stop at the traffic sign. And here you see a distribution of what the prediction step prediction steps output was. So you see that it decides to stop at the traffic light, and because we we predict that the bike will stop, we may then go straight, right? So this is very important prediction, which is usually not used for, say, drones, right? So but for cars, if you want to drive autonomously on the road, this is a very, very important step. We want to predict where others will be, right? And then finally, once we've predicted where others will be, we then need to finally find our path. So there are various algorithms. So this is essentially a search. So you will come up with various paths, and each path will have a cost, and then you will have to search between. So you'll have to choose one of those paths, like you see the car doing here, right? So there were so many paths, and then it chose a path around the obstacle so that it could turn right. Yeah, so these were the various steps, right? So you started with perception, then scene representation, then prediction, then motion or path planning, and finally control. So now we have to execute the path from motion planning by giving it relevant actuator commands like steering, brake, etc. However, I mean, like every subsystem, there will be some errors, and there are ways to fix these errors, right? So this is the modular autonomous driving stack. Now let's discuss, the pros and cons of this. So the pros, of course, are that this is modular. So it makes engineering easy because you can test at every interface of every module, right? You can divide it into teams easily and so on. What are the cons? The cons are that you have errors early on. For example, errors by the perception system will not be able to, nobody will be able to fix those errors in the later stack. So that is the con, right? So yeah, so I mean, let's leave it at that, and then let's come back to it when we're talking about end-to-end autonomous driving. Now, before we get there, I want to kind of make this point that, data-driven paradigm is something that we are very used to. And traditionally, if you had to solve a problem, you would throw a lot of experts and give them some time to come up with an algorithm to solve a problem. And today you need, a lot of data, and then you put it into a network and give it a lot of compute and hope everything works out. But at the same time, earlier, it was about, using these small tools, which all of us had access to, and we could do simple things with it. But today, if you want to do large scale machine learning, you first have to build this factory, right? Now, building this factory is difficult, it's expensive, and not everybody can do this. But then once you've built this factory, then you can build, you can then make a lot of objects in that factory through the assembly line. And what does that factory look like? So for autonomous driving, this is what our factory looks like. So what you do is, you initially start with some data set. So you start with a data set here. You train an initial model and you deploy it on the car. And then you identify inaccuracies. Now, this can also be done in various ways, right? Because you have to do this again in an unsupervised or a self-supervised way with uncertainty, with those kind of things. Now, for instance, here we found a inaccuracy that it's not working well in tunnels. Maybe in the tunnel, it's not recognizing the lane lines properly. So we will then collect data points specifically similar to this use case. Again, this how we do it, we're not talking about it, but we will do that. We will run some unit tests, and we will then give a higher weightage to those data samples and then boost it and then again retrain our system and continue this loop. Right. So this is what our factory, the data engine, looks like when you're doing an autonomous car. And especially when you have a fleet and you have these fitted sensors and a way to update your model over the air. But all major companies, Volkswagen, Benz, Tesla started it, of course, but everyone has now realized that this is the only way to crack this difficult problem. Yeah. So the way is to deploy your model as early as possible, fail, and collect those failures, and then update your model based on those failures, and then update over the air. Yeah. Now let's talk about the sensor setup itself. So, you need to have complement and redundant sensors. It goes without saying. For example, you all know the Boeing 737 MAX debacle, right? It was a big blow on Boeing. And all this happened because it did not have proper redundancy in the angle of attack sensor, right? So you need to have complementary and redundant sensors. So sensors like vision, LiDAR, and radar are all complementary and also redundant because they're all looking at the same scene. Here we did some analysis of, the sensor stack of various cars. And what we kind of found was, Tesla was the most unreliable because they also want to be cheap and, competitive in the market in terms of the car cost, because the sensors can be very expensive, especially high quality LiDAR sensors. The Google Koala has very good near field view because of the LiDAR. And this was a, Google LiDAR itself, and they do very well. And Google, the Uber XC90 also had its own problem because it misses the corners on the front. Now, a lot of you, including myself, have asked this question. So when will we see these vehicles on the road? And this is not me. This is Professor Olson from so this is Professor Olson's take on this question. And what he says is, he calls it the Moore's law for self-driving vehicles. And what on the y-axis, we have miles per disengagement. So how many miles can the car drive before a human has to take over? And on the x-axis, we have the year. Now, humans can usually do, 10 to the power 8 miles on average before they meet with an accident. And our current autonomous systems until say 2020 are at about 10 to the power 4. And if you just extrapolate it, it'll go to, 2037. But this is for level 5 when cars will be, but this is also just linear interpolation, and the world is never linear. But even if you were to believe this is for level 5 automation, where cars will be able to go anywhere on Earth. And probably this is not what we are shooting for. So I personally believe that there will only be level 4. Level 4 basically means that a car is able to drive in a geo-fenced area. And I believe that it is only that this geofence will increase, that the car will be able to go into, bigger and bigger areas, but probably it'll never be, or it'll take until 2037 maybe to get to level 5. Now, the biggest problem that all machine learning problems, specifically safety critical problems face, is this long tail problem. Now, long tail problem is basically, the problem caused by corner cases. So we want to capture the behavior of corner cases, but those by definition are not much in training data. Yeah. For example, we want to, capture the behavior of conservative drivers and aggressive drivers, but by definition, because there are not too many aggressive and too many conservative drivers on the road, the data that you capture using your fleet only, captures this part. So we have this long tail problem which we're trying to solve. Because this part was solved already in DARPA, right? So since then, we have mostly been solving the long tail. So how can the long tail be solved? One way is simulation. Waymo does a lot of simulation. A new kid on the block is Wabi by Professor Raquel Ultrason. Sorry, and they are also experts in simulation. So for example, Waymo cars until last year were doing 25,000 kilometers per day. Sorry, 25,000 cars they had in their simulators running 24/7. They were doing 10 million miles per day, and they had done more than 7 billion miles till then, right? So they've done a lot of simulation, and simulation is one way to deal with the long tail. There are open source simulators. For example, this work by Intel and Toyota, Carla. So this is something that people can look at if they're interested in autonomous driving. And now let's talk about end-to-end driving. So end-to-end kind of is a game changer in my opinion. So there's a startup from Cambridge called Wave by Alex Kandal. And what it does is, it bypasses this autonomous driving stack, and they're very successful. They're able to drive their cars in London, which is probably, one of the most difficult cities. And if you can drive it in London, maybe you can drive it at a lot of, in a lot of cities, of course, not India. But yeah, so this is what they do, right? So their system can start driving within 12 to 15 minutes. And, it's a little bit based on, the human driver corrects it a few times and then it can drive on its own. So it's very promising. Now, to do, large scale automated driving, you also need a test facility. So Waymo has this test facility in Castle, California. It's 91 acres. Also, other companies have test facilities. We at IISC are also building a test facility. So IIT Hyderabad is building a test facility for autonomous vehicles. So this is, so I'm trying to make the point that why is automated driving difficult? Because in addition to all this that we discussed, expensive sensors, expensive data, expensive manpower in terms of building these models, you also need test facilities. And finally, hardware. So you're running so many models, 10, 15 models, especially if you're doing, automated driving the first way, the modular way. You need to run a lot of these models and you need to run them in real time. So you need to have a very fast computer. And there are different players who are trying to do this. These are just two examples. So Tesla has decided to do everything in-house, including building their chip on the computer, as the chip on the car, right? The system on the car, and also their training systems. So they have one of the most powerful supercomputers in-house. Also, the NVIDIA Drive PX Pegasus is super powerful. It can do 320 teraops. And one thing to note is, why are we talking about teraops and not flops? Because we don't usually deploy floating point models on embedded devices on the edge deployment, because you don't need to. So what you can do is you can quantize your models to 8-bit, and we have found ways, and others have done so as well, of doing this conversion without loss in any accuracy. Yeah. So quantize your models and then put it onto these powerful computers on the vehicle. Now, these are various companies trying to do autonomous cars, and I've been very lucky to be associated with 5 of these. So I was associated with Apple back in 2015, and since then we've been associated with these companies as a vendor. Now, to get these cars up and running, you also need sensors. There are a lot of companies coming up which are coming up with more precise and less expensive sensors, and specifically LiDAR. So a lot of work is happening around LiDAR, and they're very good and low cost LiDAR sensors available now in the market. And this is basically the future of transportation stack, where you will, I mean, building the car is one thing, and then these are, services around it. So there's of course autonomy, but then there is all these services. So there's services, then there's safety, security, in-car intelligence and assistance, infrastructure and the connected car, intelligent manufacturing, onboard sensors, and so on and so forth. And with this, I would like to end my talk and open the floor for questions. And this is the Tesla autopilot, right? What they call the full-scale driving autopilot. It's still beta. You just cannot, it's not level 4. You still need to be, the driver needs to be attentive and aware, which is also, in my opinion, a paradox, because if the driver has let go and is not attentive, it's difficult for him to become attentive when there is an accident about to happen, right? So it's called the alarm paradox. Yeah, so with this is all I had for today, and I'm happy to take any questions.
Great session, Professor Arjun Jain. And I feel that soon Knight Rider is going to be true, and we might see some of those on the road. Well, the last time around I tried driving an automated car, it actually said, "Oh, I give up now. Can you take over?" And
hi, can you hear me?
Hello.
Okay, you can. So,
is the audio fine?
Yeah, Ankit, we can hear you. Professor, can you hear Ankit?
Yeah, so Ashish asks a question like, is location data pre-fed in urban areas with tall trees? GPS signals will be weak. Yeah, exactly. More than tall trees, tall buildings, so they lead to not very high quality GPS. So we need to do localization using LiDAR or other sensors.
Yeah, Professor, there's another question on like how does the confidence get built?
What is your estimate on commercial usage of autonomous car? One thing I forgot to mention, and this commercial usage is what reminds me. So I think it is already going to happen in long haul trucks, right? So companies like Aurora, Einride from Sweden, they're doing amazing work. So they're already doing pilots in campuses, right? In large campuses, but they're almost about to go autonomous, where they'll do fully autonomous for most of the highway, and then maybe teleoperation close to the hub, close to the exit from the highway to the hub.
Professor, are you able to hear us?
She's already asked this question, and then so Srinivas says, connected model, is there any standard body for creating trust and so on? So there are a lot of people working on it. There's a consortium in Japan led by Nissan. There's another one in Europe. So there are people working on these models, but yeah, it's mostly in the development phase. LiDAR versus radar versus camera only, which tech you see is most robust and winning in the long term? So Arvind, this is a very good question. So Tesla has decided to do camera only. I personally am of the opinion that I would go with LiDAR as well, because LiDAR is, very powerful, and every year the cost is decreasing, the form factor is decreasing, the resolution is increasing. So I think with time, LiDAR will be, a good sensor to use for such use cases. Are there any open source simulation environments for autonomous driving? Yes, Mahesh, Carla that I talked about, right? So you can download and run your simulator. It's very powerful. Your thoughts in India, specific problems on autonomous driving? Again, Arvind, very good question. So along with Professor Suresh and a few others at IISC, we are proposing a method, like we're proposing a system or a project where we will develop these things. So we have specific problems, right? So lane following is something that we don't need to do. So maybe it's easier for us. But yeah, like we drive very close to each other, maybe low speed. So there are a lot of India specific problems in autonomous driving. There are also regulatory problems.
Professor, can
for
you hear us?
For example, due to army regulations, we're not allowed to use radars of specific bands. So even the S-Class sold in India, it does not have the Distronic system, which is the adaptive cruise control system, because it uses radar. Similarly, if Tesla is launched in India, it will not be able to use its radar. Finally, can connected autonomous driving solution accelerate the autonomous driving reality? Yeah, I agree, but still, like it is also like, how do you know that this is something that that will work, right? So you always have to, you cannot trust others, right? You don't know how many cars you will be connected to, what are their observations. So currently, what we have to do is we have to trust no one and just
Professor, we're trying to reach you. I think you muted your audio.
So, Mahesh says, are there any solutions available there which only use audio and visual sensors without sensors? Yeah, so Tesla has decided to get rid of their radar. So they will be vision only, right? So there will be no radar. There is no LiDAR already, and there will be no LiDAR on Tesla in the future.
Sir, we're trying to reach you. Hello?
I think these were all the
I
questions.
think you muted your audio, sir. Could you please turn on your audio?
Excuse me, Professor Arjun.
Sorry, I cannot hear any. Oh, so sorry. I had to. I'm very sorry. Sorry, I just.
Not an issue. So technology does play roles and has its.
Because there was sound in one of my videos, so I had muted my.
We figured that. We were trying to get a hold of you for some time.
You should have just typed here. I'm really sorry.
Sure. So yeah, we were trying to have an interactive session of questions, but you have, I think, covered pretty much all of the questions.
I'm really sorry, Ankit. I was also wanting to have an interactive session, but
yeah, so not an issue. We have like few more things, and I was just expressing to the crowd that I think the Knight Rider would be soon a reality. So those of us who have grown up watching that, and there was another question on, like, between the LiDAR and the visual and other sensors, the kind of resolution that you get actually varies, and the different weather conditions in which these could be possibly working is also something that plays a role. Like the LiDAR or radar can see, but the resolution is not so good even in bad weather, whereas a vision-based thing in a fog would not be able to see pretty much like us. So I was just telling the crowd that the last time I tried driving an automated vehicle, it just hung up on me saying like, sorry, I don't understand anymore, and can you take over? So which means I need to pay attention pretty much all the time, like you mentioned. So how do we build in the trust, and when we'll see that?
But I will have to interject here. We are way over time and we are into the next session already. Thank you so much, Professor Arjun.
Thank you so much for your time. Nice talking to you.
Thank you so much for that lovely, it's very informative talk, and I think it's very, very relevant with the way we are moving into autonomy in driving. And thank you again, sir.